Hello, everyone. My name is Magdalena, and I'm a PhD student from Montana University, Leuven in Austria. And today I would like to talk about the role of shot pinning in hydrogen embrittlement of tempered martensitic steels. So at the moment, we are facing a global tendency to substitute fossil fuels with greener and cleaner alternatives. In this context, hydrogen emerged as a promising green energy source. For hydrogen to become a viable green energy source, it is important to ensure a safe supply chain from a production site to the endpoint users. And there are two major components of this supply chain, and those are the hydrogen storage and hydrogen transportation. The several technologies have been already developed regarding the hydrogen storage and transportation. However, there is one common issue, and that is the selection of appropriate materials. One of the possible materials which could be used are the high-strength martensitic steels. Nevertheless, it is well known that these steels are highly susceptible to phenomena of hydrogen embrittlement, what imposes obstacles in their practical application in hydrogen sector. To overcome these obstacles, several actions can be undertaken. In the course of my PhD thesis, we tried to change the microstructure of the steel, control the trap sites, and to reduce the permeability. The first 2 points, changing the microstructure of the steel and controlling the trapping sites, have been already successfully performed, and we managed to achieve higher resistance of the martensitic steels to hydrogen embrittlement by increasing the quantity of molybdenum carbides and lowering the dislocation density. To reduce the permeability of hydrogen into the steel, we are implementing a different surface treatments. 3 surface treatments, which are of main focus in this research, are the shot pinning, about what I will talk today, the laser-induced oxidation, and application of the organic coatings. So shot pinning is a mechanical surface modification where the stream of the shots, which can be from a different material like the ceramics, glass, steel, impact the substrate surface. This results in 2 effects. First one is residual compressive stresses, and second one is plastic deformation. When talking about residual compressive stresses, they retard initiation and growth of the cracks, decrease hydrostatic stresses, and reduce lattice spacing. All of these 3 points are very desirable to combat hydrogen embrittlement of high-strength steels. On the other hand, plastic deformation increases dislocations, and dislocations can act as a hydrogen trapping sites. And also it induces grain refinement. Generally speaking, shot pinning is a well-known and utilized method in industrial applications to enhance the strength of different components or to suppress fatigue failure and stress corrosion cracking. However, in terms of the hydrogen embrittlement, the knowledge about the shot pinning is very limited, especially in the area of high-strength martensitic steels, and results appear to be controversial. 2 materials of focus in this research are denoted here as the high molybdenum steel and low molybdenum steel. They have a similar microstructure and they differ in the content of molybdenum and a different heat treatment. The shot pinning treatments were performed using an air blast type of machine with aluminum oxide as a shot pinning media. Prior to the shot pinning of the specimens, the Allman intensity measurement has to be conducted to enable desired Allman intensity. And this is done simply by fixing an Allman strip on a probe holder, shot pinning with the desired set of the parameters, what will then induce the arching of a strip. And then by using the gauge meter, we measure a difference in the height between the flat strip and arch strip. And this gives us our Allman intensity. It is very important to mention here that shot pinning procedure in terms of hydrogen embrittlement is not straightforward process, and comprehensive optimization of parameters has to be conducted to achieve a plausible result. This you can see very well on these 2 pictures, where the first picture shows the stage at which we started. So we have non-uniform shot pinned layer, and we have a presence of a deep cracks and high percentage of surface defects. And only after several optimizations of the parameters, we managed to achieve what you can see on the second picture, and that is the mostly uniform shot pinned layer with a little percentage of the surface defects. As a rule, any shot pinning treatment will induce the surface defects. But if they are sufficiently small and residual compressive stresses are sufficiently high, they can compensate for the formed surface defects. Bearing this in mind, one can say that the ultimate goal of shot pinning in hydrogen embrittlement is to achieve balance between residual compressive stresses and surface defects. So a series of the tests were performed to characterize the shot pin surface. On this slide, you can see the results of a roughness measurement and micro hardness measurements. The roughness was similar in case of the both materials and was approximately 5 micrometers, while for the micro hardness, we can see a significant increase of the shot pinned specimens. Also, the increase is more pronounced for the high molybdenum steel, and also we can note that the highest value is reached on the surface and then it's decreasing towards the matrix of the steel, what is due to the plastic deformation present on the surface. Then to compare the mechanical behavior of the materials in air and once they are exposed to the hydrogen environment, we performed slow strain rate tests with pre-charging and in situ charging during the loading. And also we electrochemically charged the specimens, and by using the thermal desorption spectroscopy, we obtained the desorption curves. So on this slide, you can see the results of electrochemical charging coupled with thermal desorption spectroscopy. On the left side are the results for the material in the base condition, and on the right side for the material in a shot pin condition. If we take the look at the results for the high molybdenum steel, we can see that the desorption curves appear to be mostly similar. There is only slight increase in desorption rate. And for the low molybdenum steel, the situation is similar. However, the increase is a little bit more pronounced. This increase in desorption rate is most likely related to the increased number of dislocations in a shot pin layer. The results of SSRT show that in S-received condition without shot pin layer, both materials are highly susceptible to hydrogen embrittlement. However, after we apply shot pinning treatment, we exhibited the excellent improvement of hydrogen embrittlement resistance between 10 to 15%, what was calculated based on a total elongation. Also, after SSRT tests, we performed the fracture surface observation. So for the both steels, for the test conducted in air, we have a typical ductile fracture. What changes to the brittle fracture once the specimens are exposed to the hydrogen environment? Regarding the fracture surface of the specimens exposed to the hydrogen environment, the central zone remained a ductile nature, so we have a shallow and dense dimples, while on the edges of the fracture surface, we can see the characteristics of a brittle and quasi-cleavage fracture with present serrated markings. However, we can say that both alloys in general have a similar fracture modes. Then we wanted to confirm the effect of a plastic deformation, and for this purpose, we did analysis of dislocation density and grain refinement. In the first row, you can see the results of a material in the base condition, and in the second row, you can see the results of a material with the shot pinned layer. From the kernel average misorientation maps, we can see that we have a significant increase in dislocation density due to a shot pinning. And also from IPF images, we can see that we have a significant grain refinement. The similar situation is observable for the low molybdenum steel. Also after shot pinning treatment, we have increase in dislocation density and the depth of grain refinement is even more pronounced. After we confirmed the effect of a plastic deformation, so yes, we have an increase in dislocation density and we have a grain refinement. The question was what is happening with the residual compressive stresses in our materials. And for this purpose, we did residual compressive stress profiles. And we can see from these results that the highest value of residual compressive stresses was reached for the high molybdenum steel, and the depth of layer was 200 micrometers, while the lower value was reached in the case of low molybdenum steel, and the depth was 250 micrometers. So we can say that maximum residual compressive stresses decrease with the strength of the material, while the total depth of compressive stresses increases with decreasing strength. And, yep. And finally, to confirm that with using a shot pinning method, we managed to reduce the permeability of hydrogen into the material, we performed the permeation measurements according to standard Vanatkan-Stahursky cell setup. And this is what we obtained. I have today only the results for the low molybdenum steel, but after calculating effective diffusion coefficient, we can observe that the shot pinning decreases the diffusion coefficient by 1 order of magnitude. The question is, what is the reason behind this? And we might ascribe it to 2 possible reasons. First one is that we have a decrease in grain size, what consequently induces increase in the grain boundary area, and then the hydrogen is distributed more effectively. And second possible reason is that we have increase in dislocation density, which provides additional trapping size. And this brings me to the conclusions. And I will just say shortly that shot pinning is a suitable method to improve the hydrogen embrittlement resistance of the high-strength martensitic steels. With this, I would like to finish and thank you very much for your attention.